So this was the homework from Wednesday. I know that Luke didn't get a chance yesterday to do the homework. So I think this was my problem. And so we just carried it over. So this was a multiple choice problem from the 2002 exam. And it was talking about a p-value, I think. So a consulting statistician reported the results from a learning experiment to a psychologist, just setting the stage. The report stated that on one particular phase of the experiment, a statistical test result yielded a p-value 0.24. Based on this p-value, which of the following conclusions should the psychologist make? So as I'm reading the problems, I'm just kind of thinking aloud here, maybe making some mental notes. And so I wrote down here p-value of 0.24. That's pretty large p-value. So I said we're going to fail to reject the null hypothesis. Again, I really didn't even read any of my answer choices yet. I just wanted to make some quick notes to myself. If our p-value is less than alpha is 0.05, we would reject the null hypothesis in favor of the alternative, and we would say that's statistically significant. Conversely, if our p-value is greater than alpha 0.05, we would say that it's not statistically significant. So I don't know if that's going to help me answer the questions, but that didn't take me long to write, and it sort of just gets me into the problem. So the test was statistically significant because the p-value of 0.24 is greater than. I didn't even finish reading that. That doesn't make sense to me. The test was statistically significant because p equals 1 minus 0.2, 0.76. Again, that just didn't make sense to me, so I was able to cross that out. The test was not statistically significant because 2 times 0.24 is 0.48, and that is less than 0.5. Yeah, I think I understand why they're multiplying by 2, maybe two-tailed or something, but that didn't make a whole lot of sense to me either. So I'm hoping either D or E makes sense, right? The test was not statistically significant because if the null hypothesis is true, one could expect to get a test statistic at least as extreme as that observed 24% of the time. Well, boy, that felt really good to me. I really like that. I wish I could write good answers like that every time. But let's just read E just for the heck of it. The test was not statistically significant because if the null hypothesis is true, one could expect to get a test statistic at least as extreme as that observed 76% of the time. That didn't feel good. So the answer is D. That's a really nice answer. I really like the way that was worded. I think I understand where some of these, what we call distractor answers. So when we write problems, we unfortunately want to come up with what we call distractors, and those are like maybe common mistakes students make. So 60% of the kids who took the AP Stats exam this year got that right. So that's actually a pretty good problem. And again, I really like the wording of this one. So D felt good to me, and D is the correct answer. So I'm going to do hopefully a couple, 2 or 3 free response today. This stem of the problem here is the exact problem from the 2018 exam. So the stem is exactly the same. What I did is I added many more questions to this problem. So a typical FRQ in AP Stats could have 2, 3, 4 sort of questions, but typically not more than that. So you'll see when I move my paper here that there's many more than that, and that's just, again, trying to get you to think of how this year's exam questions will be different. Again, there'll be 2 FRQs, one 25-minute, one 15-minute. The 25-minute counts 55%, the 15-minute counts 45%. So they're going to feel longer than probably many, if not all, of the FRQs that you either practiced this year with your teacher, in school, or with Luke and I. So this is from the 2018 exam. The manager of a grocery store selected a random sample of 11 customers to investigate the relationship between the number of customers in a checkout line and the time to finish the checkout. So I like the 11, excuse me, I like the random. I'd feel more comfortable about just everything if it was more than 11, but it is what it is. And so I'm going to take that into consideration. As soon as the selected customer entered the end of the checkout line, data were recorded on the number of customers in line who were in front of the selected customer and the time in seconds until the selected customer was finished with the checkout. So you're done shopping and you kind of get in line and they count and there's 3 people in front of you and the clock starts ticking. How long is it going to take you to sort of move to the front of the line and then finally check out? So I kind of just looked down here at the data and saw that it was increasing, more customers in front of me a line, probably going to take longer to check out. So sort of made sense to me. The data is shown in the following scatter plot along with the corresponding least squares regression line and computer output. So I strategically picked a problem or two, I think there's actually 2, that has what we call a generic computer output. Again, these are just wild speculations on my part. Luke and I have no insider information, but you could get one of these on this year's AP Stats exam. The goal of this year's test is what we call calculator agnostic, meaning if you have one, you can use one, but you're probably not really going to need one. We know that some students may not have access to calculators, and we don't want to obviously penalize them. So one way around that is as opposed to having you type in all this data and come up with the least squares regression line in your calculator, is basically give you that. So the stem of the problem and this generic computer output are 100% identical to what students saw in the 2018 exam. So question A, what is the equation of the least squares regression line? Identify your variables. Well, even if that wasn't there, please identify your variables. So I'm gonna have to jump back and forth just because there were too many parts of my question. I said y hat equals 72.95 plus 174.4x. And over here I said x is the number of customers in line and y hat is the predicted wait time in seconds until checkout. And again, I'm getting those 2 numbers right there from my generic computer output. And so hopefully you practice that, and that felt like a relatively straightforward part of the question. Part B, identify and interpret in context the estimate for the intercept of the least squares regression line. So I guess obviously that's the y-intercept, right? And so that's the 72.95. And so I said the estimate of the y-intercept is 72.95 seconds. If there are 0 customers or no customers in line, the estimated checkout time is about 73 seconds. I don't grocery shop most weeks. My wife does it for me, but that feels okay. No one's in front of me. It takes me a minute or so to check out. That sort of felt logical and reasonable to me. Interpret in context the slope of the least squares regression line. Well, the slope is 174.40. We use that in my least squares regression line. For each 1 added customer in line, the wait time increases on average about 174 seconds. I felt confident that my answer was correct there, but I said to myself, whoa, 174 seconds, that's what, almost 3 minutes. So for every 1 person in front of me, I wait an extra 3 minutes. And then again, I don't go grocery shopping very often, but it felt like that might be reasonable, By the time the person in front of you unloads all their groceries and pays and they bag his groceries and stuff, it's on average about 3 minutes. Identify and interpret in context the coefficient of determination, R squared. So many of these generic computer outputs have what we call R squared adjusted. That's beyond the scope of the course. So I just cross it out. And so there's my R squared right there. So it was easy to find. The interpretation is a little bit more difficult, and honestly, some of my students will struggle with this. So I said R squared was 73.33%. If you had that as a decimal, that's perfectly fine, but don't combine the 2. If you want to do percents, that's fine. If you want to do decimals, that's fine, but don't combine the 2. And I said about 73.33% of the variability, that's the key word, and the checkout wait time can be explained by the number of customers in front of them in line. In a perfect world, I would want R squared to be 100% or 1. But then if I did that, then my correlation coefficient would have to be 1. And that's just not realistic. So obviously there are other factors, other variables that we haven't included that could impact how long you wait in line. But about 73% of the variation of the variability can be explained by, justified by the number of customers. Again, I'd love that to be 100%, but I realize that that's not going to happen in the real world. Calculate and interpret in context the correlation coefficient. So many problems we ask for one or the other, sometimes both. And this year again, each problem will be a little bit longer, perhaps. So I decided to ask both. If I have r squared, I can always get r. And if I have r, I can always get r squared. So mathematically, the relationship between those is pretty easy. But they do mean two different things. And so it's important that you understand how to explain in context both of those. I took the square root of 0.7333 on my calculator, and I get r equals 0.856. Again, we want students to have some sort of a calculator, but clearly a computer or something, your phone could do that as well. So I said r was 0.856. And I said there is a moderately strong positive correlation. I'll come back and talk about what we're looking for. There's a moderately strong positive correlation from a linear point of view between the number of customers in line and the wait time in seconds until checkout. So there's a pretty strong relationship between those two variables. We're typically looking for three components when you define R. You need to say it's from a linear point of view or something to that effect. We only use R on a linear model. We don't use R if we did a quadratic regression or a cubic or natural log regression. We want you to talk about the strength. Again, I said moderately strong. The adjective here is less critical. If you had said strong or very strong, we're less worried about that. And I have no set numbers that I could tell you. In other words, my kids are always saying, Mr. Murphy, if R is between 0.6 and 0.4, what's the best word? And unfortunately, I don't have one of those. So we want you to think about it. Is it strong? Is it really strong or not strong at all? Just something to that effect. So I had strength and I had linear and I had positive. So I think I got all three in there. Now be careful. Your calculator, when you take the square root of that, will always give you the positive R value. Well, R could be negative, right? R is always between +1 and -1. And your calculator can't give you that negative square root. So I had to go back and look at my data. And I said, well, if my data is increasing, it has a positive slope. And if it has a positive slope, it has a positive correlation coefficient. And so that felt good in this problem. But I have done other problems where, students were given R squared, the data was decreasing, and students almost always give us just the positive R value. So just keep that in the back of your mind. When you take the square root, it could be plus or minus, and we have to look at the original data to make that decision. One of the data points was determined to be an outlier. Circle the point on the scatter plot and explain why this point is considered an outlier. So I circled it there. And then I started to think about it. And I said, okay, there's 3 customers in front of me. I guess that, I feel like I'm going to be waiting a long time. But when I kind of went across here and said wait time in seconds, again, I'm just looking at the graph really quick, 75, 80 seconds. That feels like I went through the line really fast, right? So that didn't feel like it fit the rest of the data. The rest of the data is we had more customers in line in front of us. The wait time seemed to increase. So I said this point is considered an outlier because the wait time to check out is much lower than what one would expect with 3 customers in line in front of you. So it didn't seem to fit the rest of the trend of the data. And there's many ways to define an outlier, but that point sort of, that felt like it jumped out at me. And yeah, that didn't feel like it fit the rest of the data very well. So again, this problem is much longer than probably any problem you've done before, and that was by design. Interpret in context the meaning of this point outlier that you circled in part F. So what does it really mean? So I said for this data point, the customer waited only about 80 seconds to check out, even with 3 customers in front of them. So again, just in words, what does it really mean and what does it tell us? Why did that person not wait very long? I don't know. Maybe the person in front of them just wanted to, get change for $1, or, ask the store hours and they didn't buy a whole lot of food. And so they weren't in line for how long. No idea. I think that's the line I always want to get in, but Murphy's Law says that's not the line I ever get in. You can ask my wife about that. So again, part H, calculate or estimate the residual for the point outlier that you circled in part F. So I always write down residual equals actual Y value minus predicted Y value. In parentheses, I say AP. And I've come up with this little, I don't know, jingle algorithm. This is an AP course, right? So A always comes before P, and it seems like my students are able to remember that. So my residual was my actual Y value, which again, I'm just eyeballing that, 80 seconds. Minus 600, that's what the model would have predicted. Minus 520 seconds, or almost 9 minutes faster. So I guess this person got really lucky, right? This person got in line here, and we would have thought that they would have waited a whole lot longer than that. So it felt like they were waiting a whole lot less, which is a good thing. So this customer waited almost 9 minutes less than what our model predicted, with 3 customers in front of them in line. So again, the STEM, or the question, and this generic computer output were exactly what students got on the 2018 exam. I think there were 3 parts, and I honestly forget at this point now what 3 questions were asked. I came up with my own questions here to try to make this feel a little bit longer. And both questions this year, I think, will feel longer to you guys. So again, Luke and I are going to practice that. Luke's going to do on Monday sort of a mock AP exam. Luke and I won't be talking much on next Monday and Wednesday. And then we'll go through the answers on Tuesday and Thursday. So we want you to kind of practice perhaps some problems that are a little bit longer. Now, that problem was sort of just with one theme or thread, obviously scatter plot, least squares, regression line. Excuse me. This problem feels like it's 2 completely different themes or threads in the course. And so I, again, picked this one strategically. We're told that for each of your 2 free response questions, there'll be at least 2 major themes or threads of the course that are tested. So this problem kind of goes from, I think, experimental design to inference or something, and you'll get that this year. That much we can tell you, that much we're told. So this is from the 2007 exam. Researchers want to determine whether drivers are significantly more distracted while driving when using a cell phone than when talking to a passenger in the car. Okay, very real world problem, right? You always hear, don't text and drive, don't text and drive. I don't know how to text, so that's not a problem. I never text and drive, but I guess I sometimes talk to my wife. In a study, so I might underline that, is this an observational study? Is this going to be an experiment? I don't really know. Involving 48 people, 24 people were randomly assigned to drive in a driving simulator while using a cell phone. The remaining 24 people were assigned to drive in the driving simulator while talking to a passenger in the simulator. So I drew a little picture down here. Here's my 48 people. 24 were randomly assigned to drive in a simulator. Obviously, we don't want to practice this on the road, right? Talking on their cell phone. And then the other 24 people, again, these were randomly put in the 2 groups. That's good. They were just talking to their passenger or their friend. I think when I did experimental design, I said that these pictures here are strongly encouraged. But by themselves, they're not really going to help you at all in your answer. So we want you to in words describe what you're doing. So this was just to help me. This was just to help me. Part of the driving simulation for both groups involved asking drivers to exit the freeway at a particular exit. So in the simulator, we said, I don't know, when exit 27 comes up, we want you to exit, and we wanted to see if they could make that exit. In the study, 7 of 24 cell phone users missed the exit. So I put P hat cell phone 7 out of 24. While 2 of the 24 passengers talking to a passenger missed the exit. So I had P hat passenger talking to passenger was 2 out of 24. So those were the results from my, I guess, experiment that we ran in the simulator. My gut says those are different. I mean, no, this one's over 3 times more, right? But reasonably small sample size. So I'm in no position right now to make a decision. Is there really a difference between the two? All of this work was really just for me to, I like to say, get into the problem and try and figure out sort of what's going on. So part A said, would this study be classified as an experiment or an observational study? Provide an explanation to support your answer. So I felt it was an experiment. And so I said this study would be classified as an experiment because the researchers randomly imposed treatments. So there's kind of 2 good things, right? There's random and treatments, right? So that's sort of 2 of the components of an experiment. So I felt pretty good about that. Cell phone versus talking to passenger on the 48 people. So I think I went back and added that after the fact because I really wanted to make sure I had context. So I think my first answer was something like that. And I said, well, wait a minute. I really want to make sure that I'm relating it to this problem. Cell phones, missing exits, you know, something like that. So always, you know, go back and just read your answer really quickly and say, you know, is there any context? Is it specific to this problem? So I felt like I had to add that before I was really comfortable with my answer. State the null and alternative hypothesis of interest to the researchers. Okay, so it feels like that was experimental design. Now I'm going to statistical inference. So that's what I mean when I say there could be, or there will be, at least 2 major themes or threads in each of this year's 2 FRQs. So I asked myself 2 questions, or 4 questions, excuse me. Does this feel like a confidence interval or hypothesis test? Well, they gave me a little hint there when they said hypothesis. 1 or 2 samples, 2 samples. Am I dealing with means or proportions? I'm clearly dealing with proportions. And I guess would I read a Z table or a T table? And again, those are my 4 questions. And that's how I named the test. And that's what Luke was going to do yesterday. So I told him that I had hopefully done a good job with that before in some of my sessions. They don't ask me to name the test, but if I did, I probably would call this, you know, a 2-sample hypothesis test with proportions, or a 2-sample Z test or something like that. So I said my null, P cell phone, equals P passenger. Again, we don't want P hats here. These are population parameters. And a lot of times we will see kids put hats there, and that's gonna cost you something. That's not gonna get you full credit. And then my alternative was P cell phone greater than P passenger. I guess the researcher felt like perhaps those who use cell phones would be more distracted than those who didn't, or were just talking to passengers. That's sort of what my samples lead me to believe. But again, I'm in no position to talk about you know, whether I reject or fail to reject. That's just my gut. And sometimes I'm wrong. We always want to define the parameters. So I said P cell, that's the proportion of all those drivers who miss an exit with a cell phone. P passenger is the proportion of drivers who miss an exit talking to a passenger. So some years, perhaps that's enough, but we really want you to identify the parameters. And so I think I've done that there. So I'm feeling good about that. I'm feeling good about part A and B. Part C says 1 test of significance that you might consider using to answer the researcher's question is a 2-sample Z test. Okay, that's what my 4 questions led me to believe. So I'm feeling good, like I you know, hopefully head down the right path. State the conditions required for this test to be appropriate. So this part's really testing you on, you know, those assumptions and conditions. Do you know where to use them, why we do it, and how to apply them to a specific problem? Then comment on whether each condition is met. So we're talking about those conditions and have we met them? So I said there was random assignment to the two groups, and so that's good. So I felt good about that. Then I needed to do what I call my NP checks, you know, NP greater than 10 and 1 minus P greater than 10. And I did P hat combined here. This was 13 years ago, and there was a different school of thought then. Today's school of thought says in two sample hypothesis tests with proportions, we want to come up with P hat combined. So I think that's actually going to be 48 here when I add those two. Sorry. So P hat combined is, I'm just adding those two. So all of these want to be 48. Sorry about that. At least I caught my mistake, right? Those all want to be 48. Those want to be 48. And so I said N1 times P hat combined times N1, 1 minus P hat combined, N2 times P hat combined, N2, 1 minus P hat combined. And you'll see I get those numbers. I believe those numbers are correct. And we want those greater than 10. And well, those two are not greater than 10. And again, without going into great detail, there was a different school of thought years ago, how we would calculate those. And so those numbers years ago were actually a little bit smaller. And so it was easier, I think, for kids to say, well, those are less than 10. So we have not met the constraints of those conditions. Still holds true here. 9 is clearly less than 10. And so the conditions to meet this test were not met. And so I said the large sample condition is not met in this situation. So we did not meet those constraints. Therefore, I could not run this test. And so students, you know, my students always ask, you know, Mr. Murphy, you know, you have us check the conditions, and it feels like on almost every single problem, we meet the conditions. This is a really nice problem where we don't meet those conditions. And that's what part D is really getting to. It says using an advanced statistical method beyond AP stats for small samples. Again, I wasn't 100% comfortable with 48, you know, and two groups of 24. I would have liked that to be bigger, but it is what it is. The researchers report a p-value of 0.0683. Okay. Interpret in everyday language what this p-value measures in the context of this study, and state what conclusions should be made based upon this p-value. So now it's sort of getting back to our typical conclusions. I said my p-value is 0.0683. My first sentence, again, if you've seen any of my sessions, are pretty generic, I guess. I said my p-value of 0.0683. Since our p-value of 0.0683 is greater than our assumed significance level of alpha of 0.05, we fail to reject the null hypothesis. That right there is not enough. We're just not there yet. That has no context. That is somewhat generic. In other words, I use that every year when I teach my students. I could use it on next year's test. I could use it on next problem if I had to. So I try and finish up my sentence with some contextual component of the problem. We do not have statistically significant evidence to conclude that using a cell phone is more distracting than to drivers than talking to a passenger while driving. That's actually not what my gut said. I think way back at the beginning, I said, boy, you know, this number here was 3 times almost that number there. But really small samples, you know, this is only 2 successes, that's only 7. So that's one of the reasons why we didn't meet our conditions check up here. It's one of the reasons we didn't meet it. Then I almost forgot sort of the second part of that question. This p-value measures the chance of observing a difference in the 2 sample proportions as large or larger than the one we observed. So again, I want to make sure that I'm answering the full question. It almost felt like I would have skipped that there. So before you're done with the problem, or before you're done with each part of a problem, just go back and make sure that you're answering the problems that or the questions that we're asking. And sometimes there's multiple parts of a problem, And that almost felt like, of course, the College Board underlined "and" for me, and I should have known that there were going to be two things, and what this conclusion should be, what the p-value measures and what the conclusion. So I felt like I had the conclusion, but perhaps not what that p-value really measures. So again, I like this problem for lots of reasons. One, those conditions, we sort of didn't meet them, and so we couldn't run the test that we're used to running in this course. In part D here, that's why an advanced statistical method, again, beyond AP stats. Once they gave me the p-value, though, it felt like I was back in my comfort zone, and I could answer it similarly to how I answer other or inference questions. So here's one more. I think I'll be able to get through this one. Again, a generic computer output. I don't think that was an accident. Total speculation. I'm thinking we might see one of these this year, but I don't know, and I want to make sure that my students are well prepared if they do. So this was from the 2002 exam. Commercial airlines need to know the operating cost per hour of flight for each plane in their fleet. Okay, that makes sense. In a study of the relationship between operating cost per hour and number of passenger seats, investigators computed the regression of operating cost per hour on the number of passenger seats. That's a long sentence and there's a lot in there. I might have to go back and read that a second or third time, perfectly fine. I like to tell my students, understand this before you dive into the problem. If it takes you a couple of times to read through it, that's perfectly okay. Don't dive into the problem until you really understand what they're asking. When I did look at the graph, it did make sense. So my explanatory variable is number of passenger seats, my response, operating cost per hour. Well, as the planes get bigger, it probably costs more to operate, maybe more workers, more flight attendants, more fuel, more whatever. So that sort of made sense. Here's my 12 sample aircraft. So that sentence that long sentence number 2 made more sense when I looked at the graph. The 12 sample aircraft, I'd love 24 if possible, but 12 I guess is okay. Used in the study included planes with as few as 216 passenger seats and planes with as many as 410. So I look down here, that sort of looks like 216 and that sort of looks like 410. So these are big planes. These are wide bodies. These are planes that are flying internationally. These are big planes. Operating cost per hour range between 3,600, I guess right there, and 7,800 per hour. So it costs $4,000 to $8,000 per hour to keep these planes in the air. I can understand why the airlines want to know the operating cost per hour. Like, what does it cost to keep these planes in the air? That was a big number, and that was in 2002. Who knows what that number is now? It's probably much higher than that. Some computer output from a regression analysis of this data is shown. Okay, so I think I understand the graph here. There's 12 data points. Here's my generic computer output. We say generic because we don't want it to be any one specific manufacturer. So if you used a certain software package in your class this year, hopefully these are looking, pretty similar. What is the equation of the least squares regression line that describes the relationship between operating cost per hour and number of passenger seats in the plane? Very typical question. So if you have a generic computer output, many times we ask for least squares regression line, R squared, all of those things. So know what's on this table and how to find it. So I said y hat is 1136 plus 14.673x. And I said number of x equals the number of passenger seats. Y hat is the predicted operating cost per hour. Now, some of the different textbooks have students sort of write what these variables mean in words. So if you said operating cost per hour with a big hat over it equals 1136 plus 14.673 number of passenger seats, or something like that. You're sort of identifying the variables in your equation. That's perfectly fine. That would get full credit. Again, different books present it different ways. In some ways, I really like this. I think the book I use doesn't do that. But either one is full credit. If you use your variables, identify the variables. And if you want to sort of use the variables when writing out your equation, that's perfectly fine too. What is the value of the correlation coefficient for operating cost per hour and the number of passenger seats in the plane? Interpret this correlation. So I'm looking for R here, and they gave me R squared. So I guess we have to take the square root again. And I think I mentioned earlier, when I do that, I just want to kind of think about, could it be plus or minus here? My data is increasing here, so it feels like I want the positive value. I took the square root again. This year's exam is going to be calculator agnostic, meaning if you have one, you can use it, great. If you don't have one, you're probably going to be fine. And Luke and I, when we're writing our problems, we'll try and make them not much calculator, if at all. So I said R is 0.755. And then I really want to think about my three components, right? Linear, strength, and direction. So I said there is a moderate, so there's my strength. Positive, there's my direction. Linear relationship, there we go, I got it 3 words in a row, between number of passenger seats and operating cost per hour. So just remember, those are the, the reader is going to be looking for the number, of course, right? But also you talk about, linearness, its strength, and its direction. Okay, part C again. This felt really different to me, and it's really cool when you see it. But suppose that you want to describe the relationship between operating cost per hour and number of passenger seats in the plane for planes in the range of 250 to 350 seats. So I guess it's hard to see here. I want to look at just those 7 data points. Those are below 250, those are above 350. So let's get rid of those 5 data points. And I'm now really just looking at these 5 data points. When I do that, I see a totally different picture here. And I don't see it when all 12 of them were there, but when I cover them up, boy, it sort of jumps out at me. Does the line shown in the scatter plot still provide the best description of the relationship for the data in this range? Why or why not? Well, if I get rid of those 5 data points, this line here is not doing a very good job at all of modeling those points. Again, eyeballing it, my least squares regression line might look something like that. It's clearly negative. And so, no, the current least squares regression line is not very good for modeling those 7 data points in that restricted range that they gave me. So I said, no, the line currently shown in the scatter plot does not provide the best description of the relationship for the data in this range. This revised or reduced data set will have a negative slope and a negative correlation. So I really liked the fact that when I took some data points away, it totally changed my least squares regression line and I guess how I would analyze that, the remaining data sets. So I really like the problem and I really like part C. And your eyes don't really pick that up until you eliminate those other 5 data points. So let me get back to my PowerPoint here. I got all 3 problems in, that's great. I was a little worried about that. The first one was a little bit longer. Again, this is in all of my slides.